Hello everyone. In this section we'll be discussing what is known as induction, and we will basically be discussing this technique for proving things to do with natural numbers. So here I say this entire thing here is potentially giving you guidelines for a specific structure for a type of proof, and this is called an induction proof. So I say here to prove that a statement P of n is true for all natural numbers P. Here notice I have natural numbers including 0, but even if you were not to include 0, it would also be true, only the base case would actually be P1, not P0. Basically, you start with the first natural number, and then you can show it's true for all of the other ones after that one. So we must prove the following two cases or steps. First one is called the base case, where we prove P of 0 is true, and that's directly. Basically, you'll see that 0 satisfies that statement, whatever that statement may be. And then step 2 here is known as the inductive step or inductive case, where we prove this if-then statement, P of k implies P of k plus 1, and that statement will actually hold for all k in the natural numbers. Now you may ask, well, how do we show it's true for all k in the natural numbers? Well, this actually kind of shows it. Basically, k is arbitrary. We're not plugging in a particular number for k. We're not plugging in 3 or something like that. We're just plugging in k, and we're showing that we can do something to that statement, like manipulate that equation or whatever the case may be. Maybe an inequality, for instance. And once manipulated, it will actually imply, basically, that statement, but evaluated at k plus 1, is true instead. So k implies k plus 1. People often compare this to dominoes. So, for example, you have a domino setup, and once one domino falls, all of the other ones fall after. So a very similar idea. This is the base case, which is kind of like setting up the last domino. And then I guess, the inductive step is just hitting 1, and then that 1 hits the next one, and then it keeps going on for all of the dominoes, basically. Kind of a strange way of putting it, but definitely is effective. Now, we obviously need to see it in action to understand what's going on here. But then, before I move on to this example, though, I say, once proven, we can conclude by the principle of mathematical induction, or PMI, the statement P of n is indeed true for all natural numbers n. So remember, we need a base case, so plug in the first natural number, and then we assume that it's true for this. So this kind of interesting thing here, this is called the inductive hypothesis. I'll just write ind hype for short, but that's the inductive hypothesis. Remember that to prove an if-then statement, we assume the hypothesis. So it's called the inductive hypothesis. So we're going to suppose that for some natural number k, that statement is true, and then do some mathematical manipulation, and then we'll see that it will be true for k plus 1 as well, and then that proves it by induction. So I'll do it here. I don't have too much space, obviously, so I'm just going to give you kind of an idea, but in the next example, I'll do it more formally, okay? Not with this one, but I'll do another example more formally. So the first thing here to notice is that the base case is indeed true. So 6 to the 0 minus 1 is 1 minus 1, which is 0, and 0 is a multiple of 5, technically. 5, it's 0 times 5. Okay. And now we're going to get into our inductive step now. So let's suppose, we're assuming again the inductive hypothesis. So suppose 6 to the k plus 1, minus 1, is a multiple of 5. Okay. What does that mean? So we're assuming this, but now let's actually dive into what this means. So we can explain what this implies, and then hopefully we'll get an equation where we can maybe multiply both sides by 6. And I kind of see that here because notice if you multiply by 6, 6 times 6 to the k is equal to 6 to the k plus 1. So remember, what we want to prove, or want to show is true based on assuming this is a multiple of 5, is that 6 to the k plus 1, that's p of k plus 1, minus 1 is a multiple of 5. So notice, multiplying this by 6, at least its first term by 6, gives you that 6 plus 1, or that 6 to the k plus 1. So I'm trying to think if there's maybe a better way of describing this. I mean, again, I don't have too much space. What I'd like to say, though, is that basically this means that 6 to the k minus 1 is equal to 5 times some other integer or other natural number. Now, I can't use n and k. Those are taken. Maybe we can use m. So that's for some, let me write comma, m in the natural numbers. Okay, it's not 0 because k is assumed to kind of be bigger than 0 here. But I guess if you want to write the sub-zero, you can. Now notice if I multiply both sides by 6, I don't know if that's quite going to work. I guess it will. Let's just try it. Let's see what happens. So multiply both sides by 6, we get 6 to the k plus 1 minus 6. That's just distribution on the left. Notice 6 to the k times 6 is 6 to the k plus 1, and 1 times 6 is that a negative 6 term there. And then we get 5 times 6 times m, which rewriting it like this just shows that it is indeed a multiple of 5. So to be a multiple of 5 just means you're something times 5, right? Good. So now what I'm going to do now is I want this to be a minus 1, not a minus 6. Because p of k plus 1 is our statement 6 to the something minus 1, but instead of k or n, it's k plus 1. So I want that to be a minus 1. So simply we can add 5 to both sides. So let me just say that just by adding 5 to both sides, we get 6 to the k plus 1 minus 1 is equal to 5 times 6m plus 5. Now the obvious thing to notice here is that we can actually just pull out a 5 from this. And pulling out a 5 from that, you get 6m plus 1 multiplied by 5. But that doesn't, right? I mean, if you think about it, we have assumed that 6 to the k minus 1 is a multiple of 5, and then just using some basically algebraic manipulation, once we have an equation, all we're doing is multiplying by 6 and adding 5 to both sides, we get that 6 to the k plus 1 minus 1 is a multiple of 5 indeed also. So that shows that 6 to the k plus 1 minus 1 is a multiple of 5, assuming 6 to the k minus 1 was a multiple of 5. So that's it. We've shown that. So that then by PMI, 6 to the n minus 1 is indeed a multiple of 5 for all natural numbers n. Again, I don't have space to write that, and this is just kind of a sketch of the proof, but we indeed see the base case in action and the induction step. Hopefully we see that in action. So now I'm going to erase the board and move on to another example where we'll actually see this more formally now. All right, so this is one we've actually seen before, just we haven't seen it using this technique. So here we want to prove that 1 plus 2 plus 3 all the way up to n, so the nth triangular number, is n times n plus 1 all over 2, and that formula is true actually for all natural numbers n. Notice here I don't have the 0, and that makes sense because we don't start at 0, right? So, but still, the base case will be different because we'll be plugging in the first natural number, which in this case is 0 for that set, but it's the same idea. Base case is different, but the induction step is indeed the same. So I'll write proof here. PF is my shorthand for proof. So I'm going to take the base case first. Now remember here we're trying to show, so this is, let me just write again more formally here. This is by induction. And let me just write specifically, we want to show, or wish to show, that 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 all over 2 for all natural numbers n. So base case, our first step here. So when n is equal to 1, that's kind of our base case. Notice 1 is just the left side, and then on the right we have 1 times 1 plus 1 over 2, which is clearly 2 over 2, which is 1. So that makes sense there. And now we get into our inductive step. Where here we want to assume n is equal to k, and that will prove n is equal to k plus 1. Okay, so the induction hypothesis is that we suppose 1 plus 2 plus 3 all the way up to k is equal to k times k plus 1 all over 2 for some natural number k. Okay, so that's the induction hypothesis there. And what's kind of interesting is that really when you take a look at any statement in math that has to do with natural numbers, has to do with some formula for involving natural numbers, and let's say you're kind of noticing a pattern or something like that, and maybe it's like sequences, for example. In fact, this really is, again, the sequence of triangular numbers, and that's kind of like the closed form for them. So if you notice some pattern, you know it's true for the first few terms, and you want to say it's true for every term, well, first check as many as you can. But really what this is doing is the base case is only checking one term. But if you're exploring on your own, you want to check the first 6 or maybe 10 or however many you can. But if it seems to be true, then what you want to do is you've already kind of done your induction, or not induction, but you've already done your base case, which is kind of the checking to see that there is indeed a pattern. The inductive step is to assume for some number k, assuming that's true, then the k plus 1 statement is true as well. So that's what we're going to see right now. So I'm kind of hyping it up a bit, but here is the actual inductive step. So assuming this is true, I want to add k plus 1 to both sides. So we get 1 plus 2 plus 3 all the way up to k, and now we're adding k plus 1. So this is our kind of proving part, or manipulation. So I'm adding k plus 1 to both sides, so that k plus 1 in blue is being added to both sides of the above equation. Now, if this is true, well, notice the left-hand side is already done. If n is equal to k plus 1, we already have the left-hand side taken care of. On the right-hand side, we need to show that that works into being this, where n is replaced with k plus 1. Just so we can see what that looks like, if n is k plus 1, we have k plus 1 on the outside of those parentheses there, and then we have k plus 1 all over 2. Notice it's k plus 1 times k plus 2 all over 2. So how does that actually work out? We'll have to see. Let's do this. Let's erase that. That was just kind of brainstorming a bit. So maybe I'll keep this like that. I don't know if I want to distribute actually, but I'll keep it like that for now. I'll write that 1 as a 2 over 2, and then we'll combine. But yeah, I'm going to have to distribute, and we'll see what happens here. So let's distribute. We get k squared plus k plus 2 all over 2. Now, it doesn't necessarily look like we have what we wanted to show, but actually this factors, not surprisingly, as k plus 1 times k plus 2, which of course is indeed equal to k plus 1 times k plus 1 plus 1 all over 2. So there it is. We have shown that the sum from 1 all the way up to k plus 1 indeed matches the form, the last term multiplied by the last term plus 1 all divided by 2. So that ends the inductive step, and we can say therefore by Principle of Mathematical Induction, or PMI for short, 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 all over 2 for all natural numbers n. That completes the proof. We get a nice tombstone saying that what has been asked to be shown has indeed been shown. And now we'll move on to the next example. Right, so now we have this inequality we're trying to show is true for all natural numbers n, but not all natural numbers n, actually, all natural numbers that are bigger than or equal to 5. And I think that's pretty obvious once you start to evaluate this at some numbers and you kind of see, okay, when n is equal to 1, that's certainly true. When n is equal to 2, you have 2 to the 2 is 4, so 4 is equal to 4 then, so that's not true. What about when you plug in 3? You get 9 is less than 2 to the 3, which is 8. That's not true. When you plug in 4, 4 to the second is 16. 2 to the 4 is also 16. That's also not true. But then when you plug in 5, you get 5 squared is 25, and 2 to the 5th is 32, and here it is true. So if you're wondering why this happens, graphing actually explains a lot. But graphing actually assumes that our variable is not a natural number, but now a real number. So if you're comparing x squared to 2 to the x squared is this parabola, where 2 to the x is this function, which actually I'm not doing too much justice, but here it intersects once, And this is at x is equal to 2. That was when n is equal to 2 here. And then they intersect again at n is equal to 4. Or I guess x is equal to 4 in the graph. Now, a really nice, clever way of proving this is to show that the difference 2 to the x minus x squared is always increasing, and that, well, I guess, yeah, that it's always increasing and positive when x is greater than or equal to 5. So you can do that, but that's not an induction thing. That's just kind of calculus proof, actually. And if you kind of think about it, and again, I'm not doing it too much justice here, but let me just kind of create more space. So the parabola will go like this, and then maybe like over here, again, not to scale when this is equal to 4, that's when they intersect again. So if you look at this function, f of x, this function is actually, if you were to graph this, it would kind of look like this. It would be positive somewhere over here. Actually, from here to here is where the exponential is above, so you have bigger minus smaller. So it's going to be positive there, and then at 2 it goes down below up to 4, and then 4 and beyond it's positive. So you can actually show that this is positive and continuously increasing. It's pretty easy to show that. Just take the first derivative, and then you'll see that it's always positive. I'm not going to do that, but that's something you can definitely think about. But again, I'm going on a little bit of a tangent there, no pun intended. But that's a different way of doing this. We want to show that this is true by induction. So I'm going to be a little less wordy than I was in the previous one, but I'll still show all the steps, okay? So we're trying to show this is true for all natural numbers n where n is greater than or equal to 5. And I'll just start right away with our base case, okay? And we know this is an induction proof, so I'm not going to write that here. So our base case is when n is equal to 5, because we're showing it's greater than or equal to 5. So the first number there is 5. So 5 to the second is less than 2 to the fifth. We know that's true because that's the same thing as saying that 25 is less than 32, which we can indeed see is true. Perfect. Okay, now for the induction step. So our induction hypothesis is that we're going to suppose that k squared is less than 2 to the k for some natural number k bigger than or equal to 5. Okay, great. Now what? Well, again, this is the induction step, so maybe I'll just write that, or induction hypothesis. Maybe I'll write that here. But now the next step, again, it's a little weird because they're not always this, it's not always the same thing you'll be doing. It's manipulation, some type of algebraic manipulation. We have an inequality, so we can do something to both sides of the inequality. What I want to do is I want to, well, kind of think about what we want to show. We want to show, WTS want to show, that this is true for k plus 1. So k plus 1 squared is less than 2 to the k plus 1. So 2 to the k plus 1 is multiplying both sides by 2, but this is, so this is kind of hard to show. We have to kind of square both sides, but add 1 to both sides first. I don't know if that makes sense. Maybe we'll go with that. So we'll add 1 to both sides first. Now, but we have that square there, so it doesn't actually work out very well. Let's do this. Let's start with what we want to show. Let's expand it out. We'll get k squared plus 2k plus 1. There we go. That's pretty promising. So we want to show that this is less than 2 to the k plus 1. So we can actually add this to both sides because that's missing from the left. Again, a little bit of tinkering, and that's generally going to be the case, to actually figure out the induction step. This is like the hardest part, obviously. Everything else is kind of like copy and paste, so to speak. So I'm going to add that to both sides, so 2k plus 1 to each side of this inequality. We get that. Okay, now the left side is already k plus 1 all squared, so that's good. But now what is this? I want to show that that is somehow less than, because, so I'll leave it as is, I guess. But I want to show somehow this is less than 2 to the k plus 1. So we've kind of changed the problem in some sense. So now our want to show has kind of changed. let me erase this a little bit. So now we want to show that 2 to the k plus 2k plus 1 is less than 2 to the k plus 1. Because then we'd have a middleman in the inequality, so that would still actually work out. So this is actually, we have a little more freedom. It's a little more loosey-goosey here. So we're not quite showing this is equal to, but that it's definitely less than this. Can we show that? Trying to think if that's obvious or not. It may not be. Well, okay, so these both have 2 in common for sure. I don't know if that's going to help us or not. I guess we could say this is 2 times, okay, so this is equal to 2 times 2 to the k. But how does that help? Doubling is less than multiplying by. Yeah, that's still pretty tricky to show, isn't it? I guess we can just grab this 2 to the k plus 2k plus 1 and say that's definitely less than, you know, we haven't used the fact that k is greater than or equal to 5. I don't know if maybe that'll come into play here at all. We can definitely double this. It's less than its double. Is that always true? Is something always less than its double? I mean, yeah, that's actually always true. So, okay, so we have 2 to the k plus 1, and then we have plus some other stuff. So we've actually gone beyond our 2k plus 1. So that doesn't actually work out very nicely. So there's a little bit more to think about here. What are we going to do? So what can I do to this? Oh, we can add stuff to this. But we can't take stuff away. I'm trying to think how that works. We can add stuff, but we can't take stuff away. We want this to kind of turn into multiplying by 2. Oh, you know what? Here's something that kind of, okay, so 2 times 2 to the k, so again, we're here. This is good. But let's kind of try to explain what this means. Another way of stating this is it's itself added to itself. Number added to itself is 2 times a number. Great. So we can somehow maybe replace this with 2 to the k. There we go. So is that less than 2 to the k plus 2 to the k? If it is, we're done, because this is equal to 2 times 2 to the k, which is 2 to the k plus 1, and then we'll be done. But now, how do we show that that's true? Well, is that always true? And again, what we're kind of showing is that this is less than that. So now our want to show has changed to 2 to the k plus 1, any odd number, is less than 2 to that index. So we can actually maybe not show this by induction. I guess we kind of had to show this by induction as well, right? Maybe. Well, let's see. So isn't that just in our this is actually just our induction hypothesis, kind of. Well, not really, because there's no square there. Maybe this is actually easier to show. I don't know if it's obvious or not, but it's definitely easier to show. Notice when k is equal to 1, it's not true. When k is equal to 2, we get 5 is less than 4, that's not true. When k is equal to 3, 7 is less than 8, that's true. When k is equal to 4, we get 8 is less than 16. Oh, I guess it'd be 9 is less than 16, so that's true as well. So when k is bigger than 5, this is certainly true. Okay, but to show this, so we need to do another induction proof in this, like within this proof. It's a very good question. Well, let's just say, so here again, k is greater than or equal to 5. So let's just try to show this claim is true using induction a little bit. So notice our base case, I'm going to BC for short. When k is equal to 5, because that's our smaller number here, we get 11 is less than 32, which is for sure true. And now in our induction step, we're going to suppose 2 to the k plus 1 is less than 2 to the k for some natural number k. And now we're going to somehow show this is true for k plus 1. Well, look, so 2 times k plus 1 is 2k plus 2, which is 2k plus 3. So really all we need to do is add 2 to both sides. So if we add 2 to both sides, we get 2k plus 3 is less than 2k plus 2. 2k plus 2. Now, is that necessarily less than 2 to the k plus 1? Well, again, 2 to the k plus 1 is 2 to the k times 2, which is the same as 2 to the k plus 2 to the k. So we can say this is less than 2 to the k plus 2 to the k, and that's for sure true provided k is greater than 1, which indeed it is because k is assumed to be greater than 5. So, yeah, so the induction step has been proven here. So, by PMI, that little claim is true, so now we can definitely replace this 2k plus 1 with 2 to the k because that's certainly larger when k is greater than or equal to 5. Maybe it just takes a little bit of like taking a look at that and it's not too bad. Again, I'm kind of doing this all just on the spot here without too much preparation on that part. That's fine. Sometimes you need to see that. You need to see the thought process behind it. So I'm going to erase this. So we've kind of figured out this is definitely true. And again, the claim was that 2 to the k plus 1 is less than 2 to the k. That's for sure true. So that's been proven within that claim. And then we're done. We've proven what we've been asked to show. So let me just say, therefore, by principle of mathematical induction, n squared is definitely less than 2 to the n for all natural numbers n where n is greater than or equal to 5. Okay, so that took a little more time than I had planned, but I still want to show you one last problem that I think is actually harder than this, and let's take a look at that right now. All right, so the last thing I want to discuss here is kind of a bonus. This I actually found out on my own when I was a student, and I found no trace of this anywhere else. So I don't know if I was the first to discover it or not. But then later on I found out that this has actually been known for a while, but it was never presented like this. So it's kind of an interesting idea. And basically what I ended up doing was I looked for patterns in the alternate harmonic series, which basically this is. And I found out that if you add it to the non-alternate harmonic series, the even terms cancel out. So it's something you can kind of see, and you can see it really here. If you were to add this to the non-alternating version, the 1/2, 1/4, and so on cancel out. But then you get double this, and there's a way to manipulate things, and you end up finding out that it's actually equal to the non-alternate harmonic series, but starting at the n plus 1 term, ending at the 2nth term. So that's the other thing too, is that you have to look at the alternate harmonic series. Really, it's harmonic sum because it's finite, up to the 2nth term, so up to an even term. And I remember I showed this to a professor of mine, and at first he was hesitant and actually didn't believe me. So he just picked a random number and see if it would work in front of me. Just him and I. It was kind of intimidating. Because I believed myself, I was so confident up to that point where he wrote it down, and I was like, oh man, things are getting real. But here we go. So I'll just do what he did. So I think he did 6 or something like that. So let's write this alternate side, so the left-hand side all the way up to n is equal to 6, plus 1/5 minus 1/6. And that's supposed to be equal to n plus 1. So half of 6 is 3, plus 1 is 4. So 1/4 plus 1/5 plus 1/6. Okay. So the 1/5 is actually canceled, just we're checking here, right? The 1/3, okay, there's no 1/3. We can add this 1/6 to that side to make this 1/3. And add this 1/4 to that side, that 1/4 plus 1/4 is 1/2. And then we can actually subtract this 1/3 to this side. So now this term, and this term have been used. all we have are these two, which clearly just add to 1/2. Those 1/3 cancel, we get 1/2 is equal to 1/2. And I remember he was really surprised, and I explained to him I had a proof, but my proof wasn't induction. And actually, at the time, after going through this, I realized, okay, I could use induction to prove this, but I found the formula by discovery. So that's the other thing, is that induction is a pretty easy way to verify something is true for all numbers, but to actually arrive at the formula is really the harder part. Like, maybe you can notice those patterns, like the one we saw with the triangular numbers. I think that's a really hard one to see, but, we have different methods to getting these kinds of ideas. Like, for example, we saw polynomial fitting is a very useful one. But here, this one's a little bit different. So let's take a look. How can we prove this by induction? Let's begin our proof, shall we? So our first step is the base case. And we're just going to say this is true when n is equal to 1. So notice you can't divide by 0, so clearly we're starting at 1 here. So let's try that. When n is equal to 1, we get 1 on this side. Well, actually, it's 1 added up to 1/2. So 1 over 1 plus all the way up to 1 over 2. So there we go, we get that. And in fact, you know what? It's minus because it's actually alternating. And, come to think about it, this will actually always end in a minus. So I actually miswrote that. When I wrote plus here, it actually always ends in a negative because the even ones, notice, are negative. Since 1 over 2 to the n, 2 times n, which is even, then that's for sure ending in a negative term. So is this equal to 1 over 1 plus 1, which is 2, all the way up to 2 times 1, which is still this one too? Well, of course this is true. 1 minus 1/2 is, of course, equal to 1/2. So that's a pretty obvious statement. In base cases, again, are usually obvious. So now comes the inductive step, the really tough one. So we're going to suppose that this sum, 1 minus 1/2, all the way up to negative 1 over 2 to the k, is equal to 1 over k plus 1, all the way up to 1 plus 2 to the k, for some natural number k. So now we want to show this is true for k plus 1. So I'm going to notice here the next term would be, well, it's actually going to be 2k plus 1. So we have this whole side. I'm just going to write down the dot for that. And it'll be plus 2k plus 1. Well, that's not what we want. We want 2 times k plus 1 like this. Okay. So we need to add actually a few terms here. So notice this would be, well, maybe not a few terms, but we're actually almost done because then we would just have 2k plus 2. So that's a term that comes after 2k plus 1. And notice it's minus because we're alternating. And if you distribute this in the denominator, then you get 1 over 2k plus 2. So actually that's it. We just need these 2 extra terms. Perfect. So let's actually write that more formally now. So we have this 1 minus 1/2 all the way up to negative 2k. And now we're going to add 1 over 2k plus 1 minus 1 over 2k plus 2. And we're going to add these 2 to that side as well. So we have 1 over k plus 1 plus all the way up to 1 over k. And then we're going to add this. But I'm going to notice when you combine these into 1, what do you get? Well, you get 2k plus 2 minus 2k plus 1 all over the product. Okay, I hope you see how I'm doing that and how I'm getting this. So we have this multiplied top and bottom by 2k plus 1, we get that. But in fact, it's minus this whole thing like this. Okay. And then we have this multiplied by 2k plus 2, we end up getting a 2k plus 2 over that common denominator. And then subtracting, we get 2k plus 2 minus 2k plus 1 all over the common denominator. And then distributing, we see we get the negative 2k's actually cancel out, and then 1 minus 2 is 1 up on top. So we get 1 over this product. Okay. And in fact, I kind of misspoke here. This should have been a plus 2. All right. But is this the same, let's see, is this the same as adding all the way up to 2k plus 2? Well, if it was, then this would be 1 over 2k plus 1. So we want this to be equal to 1 over 2k plus 1 plus 1 over 2k plus 2. Doesn't seem like they're the same. Clearly they're not the same. We're adding that to both sides though. Trying to see how this makes sense. So combining those, you get 1 over this. Combining those, you don't get that. But notice, yeah, so something kind of interesting happens. We're replacing all of our k's with k plus 1s. That's a key thing. So that'll become 2k plus 1, so it's 2k plus 2 after distributing. That should be k plus 1 plus 1, so that's k plus 2. So this term needs to go away somehow. So we already have the left side, so let's just kind of expand upon the right side a bit. So let's kind of focus on the right side. So again, we're adding these two. 1, 2k plus 1 minus 1 over 2k plus 2. I'll just leave it like that actually. So I'm going to notice that the right-hand side is equal to, or I'll just say right-hand side is this. It's 1 over k plus 1 plus 1 over k plus 2 plus all the way up to 1 over 2k plus 1 over 2k plus 1 minus 1 over 2k plus 2. Now what I want to do is I want to grab this guy and this one and hopefully replace them both with a positive 1 over 2k plus 2. That should be very easy to show that because this is 1 over k plus 1 minus 1 over 2 times k plus 1 if you kind of factor that 2 out. And in reality, if you think about it, these both have 1 over k plus 1 in common. And if you factor that out, you get 1 from the first term minus that, which is, of course, 1/2 times 1 over k plus 1, which is that. And after distributing, we get positive this. So let me now erase this little bit of scratch work here. But what we've shown is what I've circled here, both actually combine to be what we need for the last term. A positive 1 over 2k plus 2. There we go. Now that actually proves what we wanted to show. So this is now true for k plus 1. So this main formula is now true for k plus 1. So therefore, by PMI, that statement, 1 minus 1/2, all the way up to negative 1 over 2n is equal to 1 over n plus 1, all the way up to 1 over 2 to the n, for all natural numbers n. Now, we didn't have time to discuss it here, and it's nothing that we're going to really see too much of, but it's just an honorable mention, is strong induction. Now, strong induction is the same as induction, only instead of assuming a base case, you assume is true for all natural numbers up to a point. So you're assuming it's true for n equals 1, 2, 3, all the way up to k, where k is some natural number. And then the induction step will show that assuming that kth term is true, the k plus 1 term is true. Now, in reality, strong induction is kind of the same, because if you think about it, assuming this is true for some arbitrary k, we're kind of saying it's true for every term before the base case up to that kth term anyways. So it's something to think about. We may see that here and there in going over some exercises in this class, but that's all I wanted to discuss here. I think the examples we saw here were enough to show the true essence of induction. I really hope you all enjoyed this. I myself enjoyed this. This is a very fantastic section, and I'll see you all in the next video. Thank you for watching.